So we said that the hardware is the real life, that's what is really happening, and we need the controller, observers to see what is happening. But inside the simulation, it tells you what's the idea of the real life, what's the results you're gonna expect, and we verified that the simulation was the same result as the hardware. We saw that in these figures. Remember these? I did my simulation and I purposely made the controller really bad. So we saw an overshoot, something like this. And this is the current. Then, with the same parameters, exactly same parameters, control parameters and machine parameters and everything, seen it inside the hardware. And after we test this, we saw exactly the same result. So we verified the simulation is same as the hardware. So why we use the hardware anyway? Maybe we don't need just use simulation. But we say the simulation is just an indication of hardware. Some models are not included here, but it gives you the idea of what you want to learn. But look at the simulation. The simulation we saw it in the slides previously. We load the parameters, then we built it inside the blocks. Inside blocks. This is familiar, the one we saw in the presentation last time. We have the control loops, the hardware here, which is representing this one with the exactly same parameters, and we get to see the measurement output here. Let's look at something interesting now. I want to run the simulation, and I see how much time it will take for this simulation to finish and give me back the result. This simulation is supposed to run for 21 seconds. 21 seconds means 21 seconds in real life. If I'm running this motor for 21 seconds, means here 21 seconds. But let's see how much it will take time for it to finish. This is already done, but I'm gonna rerun it now. So once I click here, I'm gonna click here also. Okay, now it's running. Here we have the time, but it's so small. It's supposed to be 21 seconds. You can feel the 21 seconds in real life. But here it says it's already running for 15 seconds. I look here, it's running for 4 seconds. What's going on? The computer is trying to solve everything in this and give you the results in this picture. It needs time to compute all of this. It's not like hardware. Hardware is in real time. You don't need to wait for it to compute. It's already computed. It's in the model itself, in the machine itself, in the switches itself. So while I'm talking, this is almost 1 minute, and this is almost 1 minute, and this is 16 seconds. And I'm still waiting. So the simulation will take time for it to give you the results you want. These results are similar to what we saw earlier, which are these, but in different scopes. One thing we saw in the hardware last time, I was in the control desk here, and I could change parameters on the spot. I had the control parameters, the proportional, PI regulator, integral. I could change it on the spot. We could fix the error inside our regulator. This error, we could fix it. We had some ideas from the audience how to change these. We could just put the number here, send to the controller, and change it on the spot, and we got a better result. But for the simulation here, we cannot change anything. We have to wait for the full 1 minute to simulate for us 15 seconds. So this is the simulation. Okay, so we said, all right, done. We're done from the simulation. We don't want to see it anymore. Now, Genetron told us why you don't use HIL. It will give you real time. So let's go see this HIL. Does it give us the results we want? What do we want actually? This is the simulation exactly, the result. We verify it with the hardware. If the HIL doesn't give us this exact same result, then the HIL, there is a problem in it, or there is a human problem that I entered wrong parameters. Let's see. Okay, how do we do this? Let's run. Okay, we don't need this anymore. Let's look here. I need to run some software. inside our controller, we had this program. If you remember this program that we downloaded in the flashed inside the ROM of our controller. This one was supposed to control this real hardware. And how do we connect it? We have the interface here. The cable goes inside the computer into the controller itself. Now HIL tells us skip all of this. You don't need to make all these components. You don't need any of these components. It tells you remove the connection of your controller and give it to us here, this interface. They made, I think, Typhoon made this specific interface in order for you to replace this one with this one. So these two cables are specifically in particular for our controller, and it's labeled V1B, V1A, and you give different signals routed here. Here the same thing. Typhoon gave you this specific interface for this space. So, and it's asked you here, please put these cables here, V1A, V1B. So let's do what they say and hope that they give us the result we want. With this, it seems like we just replaced what we have here, the machine, gate drivers, IGBTs inside this device. Okay, like last time, we replicate what we did last time. We had this program, we programmed this space with this one. The same thing when we control this DC motor. So we don't change anything, just keep the program as is. The only thing we change is the cable. Don't connect it to your hardware, connect it to the HIL. And if we remember, we had this control disk, which gave us the signals we are measuring. So our program in this space is already run. Let's go ahead and start measuring. I started it, and it's giving me nothing. Why? Because I didn't run the HIL. We have to run it first and tell it what it should do. There is hundreds of thousands library inside HIL, and each represent a specific model for every device. So we have to go to HIL and tell it, please replicate these things I have here in my lab. So let's go there. Once we run Typhoon, we have this screen. Let's go schematic. What does it mean schematic? It's the same thing we do in the simulation earlier here. Let's go and create our 4-quadrant DC machine. It's loading now. Okay, it's right here. Right out of the bat, we look at this one, and it looks exactly what we did here in the simulation. We had two parts inside the simulation. One is the control loops, and one is the hardware. The hardware is what? Is this. So the Typhoon asks you, what is your hardware, please? So we draw the hardware here as exactly like this one. If we come and look at the hardware here, let's just repeat so we can remember what we need for the hardware. We can just look at the hardware here. What do we need? First thing is power supply. There it is here. You can just search here Library Explorer. You can say, I want DC power, and it will give you, which is this block, which is similar to any simulation software you use. So we wanted this. What's the other main component? We need IGBT legs here. So we need how many? 2. Okay, 1, 2. What else do I need? I need the DC motor. Where it is, you just write here DC motor to give you it. And the rest of this is just measurements. What are the measurements I need? I measured the current using the CT, and I measured the VT. They are already here. I just put them here. And of course, our speed here, it's already here. You just make it exactly like any simulation profile. Once it's done, you need to configure it. What do I need to configure it? DC machines, it can be as this size, it can be very huge. We need to enter these parameters inside here. And these parameters are exactly this one here. DC motor, you open this DC motor, you will find the armature resistance, armature reluctance, same thing, you have to put it here in order for you to get the results that you wish for, which are these. Okay, if we don't put these these parameters exactly as your simulation or the hardware, it won't be the same. Then you will blame the HIL and say it's not accurate. So we put these here. What else? We have 4 gate drivers here. I just skipped them. Why? HIL doesn't need. It tells you just give me the output from your DSpace, as we mentioned before. And you remember that DSpace gives you the output of what? It takes input signals of measurement, gives you output of 4 signals or 2 signals, which are the gate drivers that you input here and give you this output. So we just specified this. I think Rosanna already mentioned this. Now we are ready, and let's compile and upload. It's the same thing as the DSpace. After we are done here, there's gonna be a compiler which generates a code. We don't need to worry about this. We just need to put the blocks, and it will upload it directly to HIL. And once that is done, okay, there is an error. Thermal bus is not gonna. Okay, I'll just rerun it. I spent like 1-2 days in order to create this file, so I'm not expert about it. I just copy my understanding of Simulink and put it here. Okay, my file. Gan? Mr. Gan? There is an error. What does it mean? Thermal network. Oh, okay. It's testing. Okay. You see here, there's a block hiding behind. All right. Verify. Okay, validation passed. Then we upload it. What it's doing right now, it's taking this model I put here and put it inside HIL to make it understand you have to be exactly like this hardware.
You want to see the RAM so sharp.
Okay, it's done.
We are making all that.
Okay. Now we can run the HIL. Once we run HIL, it will create this one inside of it. Okay, done. Now let's go to control this like last time when we were controlling this one. Exactly like it. And give it the reference speed. We remember when this one, I give it reference speed and rotates like this. Let's do the same thing. I give it reference speed in the red, and it's following it with the green. Exactly like last time, and we see the same error here, the overshoot. And the accelerate is the same, and the current voltage are the same. Okay, with my eyes I see it the same, but we have to record all this data and double check it with the simulation and hardware. It must be the same. So let's go. I already recorded this data with the same reference in the red, and we should see this overshoot here because it's the same parameter. Okay, now we see hardware, simulation, and HIL. exactly the same result. You can see the speed is behaving the same overshoot here. So, which is good. But why do I use HIL? I can just use the simulation and I don't need to pay for this 50K or something. Remember last time when I was starting the simulation, I started this timer. And it took 1 minute to be done for 20 seconds. Here, let's start the timer and see how much it will take. Okay, let's start. What do I do? What happens here? It's real time. I don't need to wait for anything. If I want the speed, I wish the speed to be 150 reference and I study the results, it's on real time. I don't need to wait. So, what's the benefit of this? I don't need to wait. I don't, and I have the benefit of the hardware. Hardware here, when I was testing it, it was real time also. I don't need to wait. I change one parameter, it's already done. So let's see now. Last time we fixed our controller. It was overshooting here in the hardware. Let's see if we change the proportional constant of the PI regulator. Does it fix the speed as well? Let's see. I'll change it to double and also the integration here also. I'll run the reference speed again and it's following it here. Does it change? Yes, the overshoot is much less. Last time we saw the same thing here. But I was worried. I said one of the participants, okay, I'm gonna change the regulator. I hope it's not stable. It's gonna be still stable. But now I don't worry because I'm not gonna burn anything if I change any parameters. I can put 1 million here and see what's gonna happen. Nothing will happen. If there is an error, it will tell you there is an error. This is not accurate. So the conclusion of this, we can replace all the hardware with HIL and see the results and change any of the parameters in real time without having us to worry. One negative here from HIL, we don't hear any noise. Last time I changed the cutoff frequency to 10 kilohertz and I said humans can hear 10 kilohertz and hear noise. There's something wrong. But here now I can change the frequency and we don't hear anything because it's all inside here. Another thing, last time I told you I skipped the heat sink here and I can touch it, I can feel it's hot. Now here I cannot do anything. I cannot touch it and they say, oh, when IGBT is hot. No, I cannot do this. I can see the things I specifically model inside.
You can put heat sensor there, is it? You can put a thermal sensor. No, does it calculate the thermal?
I'm not sure. I need to study the whole library. You know, they have huge library. I have to see everything. Another thing, I don't know who asked me. We have regenerative braking, or the current is going back to the source, and we saw here with our eyes, the voltage is going up. But here, if I observe the power supply voltage while braking, it won't go up. Why is this happening? It's not its fault because when I modeled my circuit here, I put here power source, which is DC constant. I put please be constant at 120, so it won't go up or down. So that current which is going back to the source is just disappearing because you already asked it specifically to be constant.
You can put terminate resistor.
Yeah, you can put that, or you can just find here in their library. I hope they have it. They must have it. The right battery here. Oh, they have it. Just take this battery and put it here. I didn't test it yet, but you can. I guess yeah, because you can save the SOC of the battery and our capacity and everything. So when the current is going back to the battery, the SOC will increase, and you, as a consequence of that, the voltage will increase. But I'm not sure if this will happen. So yeah, that's the HIL. You want to add anything?
Yeah, for the commercial info, right? So just now we have seen that grey color. So the one is a model for Hill 44. The one is a model. That one is an upgradable model from Hill 42. So the red one is the HIP402, is already EOL. So we currently replace the new one for the HIP11. So the price is much more cheaper than 44, which is started from 50,000 ringgit. And the license is perpetual, it's free. It comes together with the hardware. And also, but there's limitations a bit for the HIP11 because of HIP11 it consists of 3 cores, 4 cores, and another 2 high-end model, which is the 604 and 606. This is a 6 cores and 8 cores. So yeah, I believe that Mr. Gan already shared software. So I hope that you guys can try, explore, because we have the many modules inside for you guys to explore with examples of the application. And yeah, maybe you can try mix and match and try to compile everything. So if you have a problems, just let us know so we can help. Yeah.
Okay, thank you, Shafiq. If we have time, I can show another application. Maybe DC motor and the model of DC motor was faked here. So let's check inverter. Dr. Julia showed us hardware results earlier, and let's try to recreate that. First thing, we just need to upload the program to the DSpace, which is this one. This program is basically to have an inverter. Let's go ahead and upload it to our program. Now this program is inside DSpace. DSpace is outputting signals in order for it to control an inverter and give us sinusoidal, the ones we know. Let's go to Typhoon, go to schematic editor, and make up this inverter. Typhoon just made our life easier here. They said, you want inverter? There is one. Here. We give you the whole inverter block with this 3 of these inside here. You don't need to put each leg individually, but you can do that if you want to play around. So after this is done, we upload it to HIL in order for HIL to stop imagining that or modeling this inside of it to this one. Let's upload this one. These steps, it might be confusing, many steps, click, but it's very simple. Anyone can do it. You have a bachelor student or anyone can do it. You can bring anyone from the street with degree. So let's sit here, please draw this one.
After my complicated.
Because it's just blocks here, you know. Yeah, just Lego, put blocks and it's done. Okay, this is the inverter. Let's run this. We are already telling this one, please be inverter. The schematic we already shown here. Now let's run it and see if we have signals we want. Alright, let me double check. This is just scaling to see it exactly. Okay. Dr. Julia, I think in the third session, first day, showed us this screenshot from an oscilloscope. In this one, we can see in yellow, very ugly sinusoidal, but it's sinusoidal. Voltage, the yellow, the green is the current. If we focus here and come read the scale, this is around, I think, 6 volts, and this current is around 0.1 ampere. For her load resistance and so on. We must see this with the exact parameter here. So it is the same one. So HIL, we just verified HIL can do an inverter accurately and can do the DC motor with all these connections accurately. The same thing. In real time, I don't have to click and wait like this, then I don't like the results, I have to change another parameter, stop it, click again, run it, and wait. Usually, okay, last thing, sorry. I had to previously run simulation for a car to determine how big the battery pack do I need to achieve 300 kilometer range. In order for me to run one simulation of this with one specific battery, I needed around 8 hours or 9 hours. So what I did, I have 4 computers, 2 at home and 2 here, and maybe one of my friends. I connect them all remotely here in order for me to run 4 simulations at the same time to determine the size of the battery. If I had this HIL, and they already have an example model of a car with a battery you can specify, it will be in real time. I don't have to wait 7 hours to know that the battery size the one I need. So yeah, this is the HIL.